Welcome. I'm Bill Wake. This is our weekly summary of Twitch, and this past week we've been starting a program in assembly language called 10th. What it is going to be a stack-based programming language running on a threaded interpreter written in ARM64 assembly language. So I wanted to try this technique of a threaded interpreter for a while, and this is a chance to do that. So Monday we got Hello World working. We figured out the calling sequence, and we took lots of notes. Tuesday, we wrote a little test framework and got string length working. Wednesday, we put in a print function and improved our test framework. And then Thursday, we kind of ran around trying to figure out a way to create jump tables or indirect references to code that we can relocate. The first day was a lot of note-taking and capturing what was going on, trying to figure things out. We took notes about the calling pattern, the register usage, addressing modes, a couple of cheat sheets, you name it. But we got Hello World running, and that's always a big step. Then we worked on this test framework, and the way we're going to do it, at least for starts, we've got a macro for test start and one for test end. With test start, you give it the name of the test, and then it'll create a label for that name, LTS, whatever you gave it. So here's a little test. There's a routine called add, and we're going to call... we're going to set x0 to hold 2, x1 gets 5, call this add routine, and when it's done, x0 should be 7. The result is always an x0. To run the assertion, we're going to put the expected value in x1 and a link to the name of the test in x2 and call the assert equal method to do the assertion. Test start is a macro, as I mentioned, and so it creates the name of the test as a label. It does strlr, which is a procedure prologue. It sends the test name to a print statement, and then it exits by branching to the no op at the bottom in line 18. Between those, we have the test name as a string so that we can use it for printing. The test end macro is just doing basically the pop on the stack so that it can get the right register back and a return. And finally, the assert equals. Its basic job is compare x0 to x1, line 8 there. And if it fails, we're going to go down and capture the failed message as the message to print. Otherwise, we'll capture the pass message as the message to print. We go to exiting where it starts printing and then does its normal return. On the bottom, you'll see the two messages for pass and fail. The escape codes give it color. And here's what happens when you see it running. You see test 1 pass, test 2 pass, and then run a different one. Empty string length 0 passes, nose length for non-empty string passes. If one had failed, it would be a red, the word failed in red. At the beginning of the first test, you might notice there's a blank line. We're testing a procedure called new line, and then there's a hello leftover from our early Hello World tests. So you get a mix of the output from your program and the tests, depending what you run or print. Kind of like XUnit, I guess. Given the test macros and the assertion, we were able to write tests for string length. So string length is going to get the length of a C-style string that has a 0 terminated value. So a 0 byte for the last one. And we get the input comes in x0 is the pointer to the string. x1, we're going to copy the pointer and then use x0 as the counter since that's the return value. And you see the loop, and at the bottom, the branch loop. Really, the loop is just walking byte by byte. If it's 0, it returns with whatever the current count is. Otherwise, it increments the count and goes back around. So not a very hard method. There might be a better way to write it, but it gives us a string length, which is handy. We went on to do print of strings only. And this one's a slight bit more work maybe, because it's going to depend on string length. So 3637 is the name in the prologue. And then we're saving x0 because we don't want to lose it when we do the string length. We call the string length routine. It gives us back the length of whatever's in x0. And then we're going to set up a procedure call or a service call. So line 47 is the service call, and you can see we're loading in the arguments. So x2 is the length of the string, x1 is the pointer to the string, x0 is the code that says which file handle do you want, and 1 is standard out. x16 is the service code. So for a write in Unix on the Mac, you use service code 4. Unfortunately, current versions of Linux use a different mapping. This is another, I don't know, a different Unix mapping, but it's kind of unique to that. All right, and then a post epilogue to return. All right, so now we have a function that calls the function that's doing some work. So we're getting some leverage finally. All right, now I mentioned this idea that we want to be a threaded language, and one of the approaches for that, there may be others, you have routines that are primaries, and those are written just as a normal assembler routine. In the big block on the left, you can see code going on down to ret, which is the return. And so if you have normal assembly code, use that, and that's the primary. Now, it's embedded in a record structure. This is to manage a dictionary of names. So it's going to be, as an interpreter, it's going to have to do a lookup of things by name, and it does that by walking through a linear list. Okay, and the headers, the name of the routine, a link to the previous element of the linked list, and then a pointer to the address of the code we want to run. So the pointer is really just pointing one instruction down to the code itself. Okay, and so this will be used when we're calling from secondaries. They need to know the address of the code to run. So the secondary, the core of that is a list of other addresses, the other primaries or secondaries that are being called. So it can call itself recursively even, but that list, something's going to walk through that list, and that's the start2d routine. It's going to walk through that list, keep track of where we are, and as we call things, it moves on to the next one until finally we get to the end-to-end, a link to that. End-to-end is going to be a primary routine that manages returning from a secondary routine. And between those, we'll be able to call all our secondaries, which will eventually call down to primaries. It's always primaries at the leaf. Okay, we tried to implement this, and the last day of the week was kind of the hardest because we just could not get it to work the way we wanted. So you can see line 6, we're putting in the name header. Line 8 is, it's going to be, we're moving around trying to decide how to build the best header, but that one doesn't mean anything at this point. Line 10 is the link to the previous one, and since this is the first one in the linked list, it points to a nil or 0. And then line 11, we're trying to get a pointer into the code. So dot gives you the address of the current instruction, which I'll pretend the lines are instructions. It's instruction 11, and then it moves forward 8 somethings, 8 bytes, and gets to the NL, the new line routine. Now the dot plus 8 will work. It's if we dump out this object file, we can see it pointing to the new line routine, but the value it puts in is just that address of the new line routine, and it's not a relocatable thing. So when you take these object files, you'll build them to a big executable. It has to take each object file and figure out where it's placed and adjust anybody who references that. So anybody who calls NL from another file, the linker decides what addresses that will really have. So pointing to line 16 isn't good enough, because if you're just pointing 16 instructions in, you don't know where this thing's going to end up, and it's not going to end up at 0, so it's going to be wrong. So it's a challenge. Now we tried dot plus 8, we tried NL, using the label, we tried equals NL, we tried whatever we could think of to get something relocatable. And this process is put something in, do an object dump, verify that it's got the right address, and we looked at the object symbol tables and then build the executable and verify it's got the wrong address. Okay, and most of those did. So we had to come up with some other scheme. We tried several ideas, but the one that we wanted to go with is one from MudTruck666, is a regular viewer, and suggested, hey, let's just make a sort of jump table with procedure calls to these addresses. And we'll be able to take those, and at runtime, we can fill in the table headers, for the symbol table that we're going to walk through, we can walk through and just pop in those addresses where they need to be. And that seemed like a reasonable idea. The problem or the challenge maybe, because it will work, the challenge we have is the BL instruction doesn't use addresses the same way. I mean, addresses can be 64 bits, and the instruction itself needs some room. So it's clear a 32-bit fixed width instruction is not going to have 64 bits of address in it. And the way it works is the first two characters are telling you that it's a branch linked, and then the FFFFA is really a negative number, and this one is -6. So from 3ED4, you go back 6 instructions, you'll be at the NL. And I put the second NL in so you could see it's got a different number. FFFF9, okay, is -8 because we've moved 2 steps further forward, and we have to compensate for that. So as you're going through to take this table, which we can generate and get a link to, we're going to have to walk it, but then adjust as we go through, not just filter off that 9.7, but, and add in the FF that makes it a negative number, but adjust that relative to the current position starting at 3ED4 in this case, to get a true address value. You may notice the last one, 94003, that instruction, the start, actually got placed right after the table, a little bit after, and only 3 instructions down. The forward ones show up as 00s, and the backwards ones show up as FFs. And I think that last difference between 94 and 97, there's 1 bit difference that tells whether it's a negative or a positive. So I think we'll probably be able to figure out from that which thing it is. And anyway, with this information, I'm confident we can build the table like our primary one, with those links and all that. I think that should be okay. We'll just have to go through and stuff where it says address of code and pop in these addresses as we find them. So that puts us kind of ready to move forward on this. If we can build these tables, I think we can build the ones on the data side, the secondaries, more easily because they're not going to get relocated or anything. All right, so next week, we're going to implement stack operations, push and add. So those are language level operations, the primary routines or primitive routines for 2 of our stack-based language words. Push will push something on the stack, and add will add. To do these, we're going to have to figure out the data stack and where it's going to live and how to get to it and all that stuff. Again, I think we'll get there. And then to make this run as a secondary, because it's going to be a defined action, then we're going to have to implement the table wrapper around it, the header and so on, and the interpreters start to end or start to and end to, and whatever they were, start 2D and end 2D, I guess, to implement those so they know to walk through as a virtual program counter and keep track of the steps and make that all hang together. And then getting those, if we get that far, we're going to work on the overall interpreter. We want to be able to make sure we can call primaries from secondaries and so on. So I think we have some fun to look forward to. Hopefully not all as painful as Thursday was. All right, if you'd like to join us, we're on Twitch 2 to 4:30 Eastern Time daily, or 7 to 9:30 p.m. UTC. If you want to catch it live, that's xp123.com/Twitch will take you there. Or if you want to see old sessions, xp123.com/YouTube is there. They're time delayed and lightly edited. I think they're about a month behind, a few weeks behind anyway. All right, well, take care. Thanks for watching. Bye-bye.